All right, so for my talk today, I'm going to tell two different stories. Both of these, like Brittany mentioned, are oriented around doping nanomaterials. And in the first talk, I'm going to discuss more work for my PhD, where I was trying to introduce dopants into a very covalent material that was hard to diffuse dopants into and strategies to accomplish that. And then in the second part of my talk, I'm going to discuss some of my postdoc work, where I was trying to introduce trivalent metal dopants into perovskites to create these very luminescent materials. Those are a lot of very jargony words that I'll explain more in the talk. But in this system, there were a lot more easily formed dopants, and because of that, there were a lot more opportunities to engineer new materials and new processes. So that being said, first, I'm going to go over a very broad background about doped nanomaterials in general. There are a wide range of applications, and just to cover a few, for example, some groups are working to engineer the absorption of nanomaterials by changing the number of charge carriers in them. This has led to applications in photothermal therapies or drug release, where you can shine a laser on materials whose absorption has been engineered to either induce cell death or to release some kind of drug or therapeutic. Other applications include electrochromic windows. Similarly, other applications of doped nanomaterials are quantum sensing and information, which I'll talk about in more detail a little bit later on in the talk. And then another application is something where you'd use nanomaterials for confocal imaging. These would be sort of the stain material that you would use as a luminescent down converter. Similarly, these can also be used for extreme up conversion to do super resolution imaging of a wide range of different materials. And then finally, one last application that I'm just going to mention here is a very general category called spintronics, where now you're trying to use the spins in nanomaterials and engineer those to do some kind of information processing. These are all very general and a wide variety of applications, but the common theme among all these is that they all involve different doped nanomaterials. For example, this could include alloyvalent and p-type dopants that are used to engineer the absorption of plasmonics. In the case of quantum sensing and information, this involves luminescent color centers, that is, energy levels that are incorporated within an insulating material. Similarly, defects are used to enhance up conversion and down conversion. And in spintronics, defects can be incorporated into a lattice to introduce new spin states. I know a lot of those were also very jargony words. Let me take it another step back for everyone that hasn't had a condensed matter class in maybe ever. On the right, you'll see a crystalline material. Very generally, whenever you have a crystalline material, you'll form a continuum of energy states. And depending on the state of that matter, the energy states are distributed differently. For example, in a semiconductor or an insulator, you'll have a continuum of states where you have that are full of electrons. We would call this the valence band, or you may also think of this as the highest occupied molecular orbital. There's then a region of forbidden states known as the band gap, followed by another region of electronic states that are now unoccupied. These you may more commonly think of as the lowest unoccupied molecular orbital, or the conduction band. Now, if you shine light at a material with energy greater than the band gap, this can drive an electron into the conduction band, which can then rapidly thermalize to the band edge. And then, if it's allowed, this can emit luminescent, or this can emit light. In this case, you could, for example, have absorbed a blue photon and then re-emitted a green photon with a significant Stokes shift. While this all sounds very complicated, you can define and track all of these processes with fairly simple differential equations. And so this is really just a zeroth order rate reaction in this case. And you could have done this and understood the math after Gen Chem, or really incredibly well after reactor design. If we were to remove an atom in the lattice and replace this with a dopant, this picture changes slightly. This could, for example, introduce a new defect into the lattice, which could occupy a new state. This can then be accessed. So if you were to excite now a nanomaterial or any material with a defect in it, energy would be, or the electron could thermalize, and then the energy could be transferred to a defect state where it could emit. So now you can imagine you have this material that used to emit green light that now emits red light. However, you could also imagine that these occur in competition with each other. And so depending on, quite literally, the reaction rates or the kinetics of this process, you can have a various ratio of red to green emission depending on the defect structures that you introduce and the band gaps of the material, which are all extremely tunable whenever you're working with nanomaterials in particular. Another trick of working with nanomaterials is that the different lattice sites that exist within the material are now quite different. You can imagine that a lattice site that's very close to some kind of air, solvent, or ligand interface has a different energy than a lattice site for a dopant that's deeper in the lattice. And so these can produce different energy levels within the resulting material. This means that if you randomly introduce dopants into a solid-state lattice, you could end up with a distribution of energy levels. And now you could access different energy levels, or really you would always access typically the lowest energy level among these. And so you would perhaps only see some subset of dopants in the material that you're working with. If, for example, some of these states have different symmetries than others, these could also lead to different splittings in a magnetic field and different spin properties. So with that very general background in mind, let me talk now about how exactly we dope nanomaterials. And for the first part of my talk, I'm going to focus on this case where we're trying to kinetically trap dopants. This is a case where atoms don't freely diffuse in a lattice. That is, if you're trying to get this green dopant into a particular lattice site and you just heated it up, you can't get it into the lattice because there's no strong diffusion in the material. These bonds are just too strong. And this is the case whenever you have a very low diffusion coefficient. Ideally, however, your defect that you're trying to form is at some point metastable. On the far end of that spectrum, you have an ionic host which has a very high diffusion coefficient. And ideally, the defect you're trying to form does have some kind of low energy structure. In this case, you could imagine just putting your defect nearby the solution and chemical potential would drive it into the lattice. But the problem can still be complicated where, let's say you want to form one particular kind of defect in the material. If you're stochastically introducing defects into random lattice sites, it's unclear whether you'd always be able to form the desired defect in a very complicated and material that has an extremely high diffusion coefficient. This needs to be one of the lowest energy defects. But first I'm going to talk about this case on the far left side, where you have materials that have very low diffusion coefficients. And the example for this in particular is diamond. And the application of this doped diamond is largely quantum sensing. So first, why do we care about doped diamond? I gave it away a little bit. We care about it in part because of quantum sensing and quantum applications. But another reason that diamond is a really incredible material is its really high electron and hole mobilities and its very wide band gap. Because of the high electron and hole mobilities and the wide band gap, diamond would make an incredibly promising material for high power and fast switching electronic applications. It could isolate a lot of voltage over a very thin material. The challenge with making doped diamond and making diamond electronics in general is that we don't have a very good N-type dopant. The usual suspects of N-type dopants tend to form maybe incidentally mid-gap defects, and the ideal defect would sit very close to the conduction band in diamond. This is sort of what we're trying to form in this material. In addition to not quite forming the right energy levels, all of these materials are diffusion limited, meaning like that green atom earlier, they're not going to go smoothly into the lattice. And so we struggle to even form these defects, which often don't perform very well at all. I'll say there was one success story, which was Boron Dye Deuterium. This was sort of a rare case, and it worked because both boron and deuterium could diffuse easily in a diamond lattice. The problem was that this lasted for about 4 hours at room temperature, and so I don't think we're going to have some huge change in the industry working with this defect in particular. Now, that being said, there are some theoretically proposed defects. For example, this lithium tetranitrogen defect and this nitrogen silicon defect. However, if we're struggling to get a single nitrogen atom into the lattice, it seems pretty incomprehensible that we could manage to localize 4 nitrogen atoms and a lithium atom onto one lattice site. So these are theoretical, but it seems pretty far-fetched we could ever actually form these. Now, the other large application of diamond, like I alluded to earlier, is quantum sensing. And to do this, we're trying to form color centers in diamond. There are 2 defects that I think are particularly popular for quantum sensing in diamond, and these are a nitrogen vacancy center and a silicon dye vacancy center. This nitrogen vacancy center is formed by simply removing 2 carbon atoms from the lattice and replacing one of these carbon atoms with a nitrogen group. And we typically talk about the negatively charged version of this atom. Using the nitrogen vacancy center, groups have been able to do some pretty incredible things, like measure local magnetic fields on a substrate with now nanometer precision, looking only at the luminescence from these nitrogen vacancy centers in diamond. Similarly, this silicon dye vacancy center is an incredibly popular material due to its very narrow zero phonon line for applications in quantum sensing, in quantum information. Now, if you took diamond and you took a substrate and you simply ground it up, you would actually get nanodiamonds. These nanodiamonds are incredibly biologically inert, meaning that they'll move freely through cell walls, and that they can then act as luminescent sensors within living cells. This means that not only can you do these same kinds of complicated quantum sensing applications on a diamond substrate, but you can also do this inside of a living cell. Sorry, that's not showing up incredibly well in this light. But you can, in this example, a group was able to measure temperature using quantum sensing from a nanodiamond that was floating inside of a living cell. Now, the challenge of doing this is the low diamond diffusion coefficient, but it's also a bit of an advantage for dopants and diamonds. Because of the very low diffusion coefficient of diamond, if you heat up a sample of diamond containing a dopant, it'll simply stay where it's put. This means that you can optically address that single defect again and again very reliably. This also incidentally had sort of surprising applications in solar, in understanding the origins of the universe. It turns out that the primary pre-solar material that exists whenever a solar system is forming is actually nanodiamond. And the US has actually sent up a satellite that then flew it through the tail of a comet to intentionally collect these nanodiamonds. It turns out that these defects that form in diamond are so stable that they can then take these diamonds back to Earth, measure the elements that came out of them, and then use these sort of as these tiny time capsules to understand how the solar system itself was forming. That means that dopants that were introduced in diamonds can stay there for millions of years if you're not careful. And that's convenient in some applications, but if we're trying now to get our dopant that into the system, I think this just illustrates how hard it can be. For example, if you wanted to get nitrogen to diffuse into a diamond lattice, nitrogen diffusion won't occur until about 2000 Kelvin, but you stop having diamond at about 1000 Kelvin because it is a metastable material. It's not great. The primary way of making nanodiamond, there is one, fortunately. There are a few different pathways. One is actually detonation. It's a way of getting rid of old TNT. They can take TNT in the presence of random carbon precursors, ignite the TNT, and then within the shock wave, you tend to nucleate small domains of nanodiamond. You can intentionally dope the nanodiamond this way, but you also seem to accidentally put in a ton of the periodic table into the sample as well. And so again, getting 4 elements or 5 elements on one lattice site, completely out the door. Similarly, there are other plasma-based processes where you can put some kind of carbon precursor and some kind of dopant into a plasma. This will form diamond. As you begin to introduce other defects, though, or other dopant materials, these are completely scrambled within the diamond sample. And so again, you're not going to be able to localize any defects onto one lattice site. And in particular, I did a lot of work trying to track down some syntheses of these and found that a lot of groups that thought they were making diamond were actually just making copper covered in carbon and things like that. So some of these are sort of bogus syntheses as well. Though it is a viable way of making diamond, I should say. Last, and perhaps the most successful way of making doped diamond is actually with ion implantation. This is a mechanism where you can take a substrate of diamond and you can literally launch an ion at it. This will break through the carbon lattice and implant in the diamond. And this is somewhat deterministic. But you can imagine that you now break up the diamond lattice. And again, there's still this trouble where you're not going to localize more than one element onto a single lattice site. So our pitch for how to solve this is to dope diamond whenever it's convenient to dope it. And that is, by that I mean to introduce dopants into an amorphous carbon precursor before it's diamond, and then convert it into diamond. Our hypothesis for this would be that if we introduce some small molecule with a given stoichiometry, and then we convert that small molecule containing amorphous carbon into diamond, that provided the small molecule doesn't break down too much, we might be able to localize now 4 atoms defined by that small molecule in our diamond sample. You could also imagine that we could now control the size of the diamond by varying perhaps the size of our carbon precursor starting material. And it'll make a little bit more sense later on, but we can also potentially, we want to heat this with a laser, so means we could also potentially pattern diamond in different ways onto a piece of carbon. Now, the carbon precursor that we want to, or the precursor that we want to use to make these nanodiamonds, we need a nanostructured carbon starting material, and the one we want to use is carbon aerogel. This, at least for a large chunk of time, was the lowest density material that had ever been made, and it's fairly straightforward chemistry. You can simply take resorcinol and formaldehyde, mix it together with an acidic catalyst and acetonitrile, and then add in some kind of dopant structure. Very quickly, this will undergo a condensation reaction to form effectively a skeleton that looks sort of like this. You can see these very small domains that are a little under 10 nanometers in diameter of carbon. We can then exchange our acetonitrile with ethanol, dry it with supercritical CO2, and then pyrolyze at a high temperature to drive off all of the oxygen bonds, which lets us end with this very dark structure at the end. This is really just showing how much light all of those small grains of carbon absorb, and the fact that any scattered light really just goes deeper into this network of carbon sol gels. We also use this as a platform to make new supercapacitors. So we're able to take that same carbon aerogel and introduce transition metal dichalcogenide sheets. I'm not going to talk about this project, but it turns out this was a very scalable way of making supercapacitors, and it was a fairly interesting project. That being said, we have our carbon aerogel. We think we have a way of doping it, but how do we reach high temperatures and high pressures to actually form diamond? The tool that we want to use is called a diamond Anvil cell. So now, to be clear, we're using a tool made of diamonds to make more diamond. These are not the diamonds we're going to end up with. In this tool, you're actually using the mechanical properties of diamonds that lets you reach a very high pressure. And in particular, what you do is you would align two diamonds directly facing each other so that the small tips of the diamonds, known as the culettes, are perfectly planar to each other, and then you push them together. Because this is a very small surface area, and you're exerting a very large force on the diamond, you're in effect producing a very high pressure on the sample loaded within the chamber itself. So our plan is to then put in our sample, our carbon aerogel, as well as a ruby. We use the luminescence from the ruby as a sensor of pressure inside of the high pressure chamber in the diamond Anvil cell. And then we flow in liquid argon, which quickly condenses into solid argon at these high pressures. This is effectively a fairly non-compressible medium that allows us to exert hydrostatic force evenly on all sides of the carbon aerogel. And then practically, this is what one of these tools can look like. And you can see the diamond sort of sitting right in the very center of the sample. One important thing to note about the argon is that in general, groups have used argon and other noble gases because in theory, they should make very excellent pressure media because they're hydrostatic at high pressures, and most importantly, because they're supposed to be chemically and physically inert, but we'll see that that may not be the case as we move forward. And then just very briefly before I get into some results, this is the carbon phase diagram. It's a fairly complicated phase diagram because the transformation from graphite to cubic diamond is very kinetically limited. And in effect, it's much easier often to work with amorphous carbon and convert that to diamond. So that's sort of these purple data points or different data points where you've been able to convert amorphous carbon to diamond. These experiments take place or are generally in the phase range of about room temperature up to 3,000 Kelvin, and then between about 15 and 30 gigapascals. So this is practically what one of these samples looks like whenever it's loaded. We have a large piece of, well, I swear there's a large piece of carbon aerogel in there. Oh, man. And then filled around the outside, it looks mildly transparent. This is all solid argon around it, and this is loaded at 16.3 gigapascals. After heating, there are these lighter gray areas that I think you can see on there. And so the first time I made diamond, I thought it would be really cute to try and draw and show that I could pattern this. Since we're trying to irradiate this to reach high temperatures, we're shooting a fairly high-powered near-infrared laser at the sample. And so I tried to sketch out a diamond of diamond in a diamond Anvil cell. Usually you can see it a little better. Maybe it's best you can't see it that well because I don't think I did the best job, but it was an attempt. More practically, this is what we show whenever we publish the paper, which is that if you heat at different power is you can change the line width of diamond that you form. You can see that as you increase the power, line width increases overall. And for what it's worth, this seems to be the highest reported resolution of carbon to diamond phase conversion that's ever been demonstrated. I don't think we realistically have a great application for that, but we've been able to do it, and I think that's interesting if anyone has ideas. So we can be sure that we've made diamonds in a few different ways. We can look at Raman at pressure, where we see the occurrence of this peak related to diamond. We can take the diamond out of the diamond anvil cell and do Raman, where we see this very strong peak associated with diamond. Notably, we don't see any sign of graphite in that Raman signal. Similarly, we can take this and put it in a TEM. We can do electron energy loss spectroscopy. The notable feature here is this dip, which is very characteristic exclusively of diamond. Similarly, we see this very small feature, which might indicate some kind of surface graphite, but really this appears to be almost entirely diamond. Also, we can look directly at the material in TEM, do diffraction, and again, we only see diffraction peaks associated with cubic diamond and no graphite. So everything we look at points that we've made, or points to the fact that we've made diamond. Now, to test the hypothesis, we want to see if we can dope this diamond by initially doping the carbon starting material. To do this, we would take one sample, mix resorcinol, formaldehyde, and TIOS, which is a tetraethyl orthosilicate, a silicon-containing small molecule, form our carbon aerogel network, and then convert this at high pressure, at high temperature, into diamond. We can be sure that we formed some introduced some silicon by looking at EDS of this sample. And then we want to run a control, where we look at an undoped carbon aerogel and see the defects that have formed. So first, if we were to just make diamond from our undoped carbon aerogel, and we look at the photoluminescence of that material, we see this very broad feature that luminesces whenever we shine light at it. And this is actually characteristic of that nitrogen vacancy center that I mentioned at the beginning of the talk. You see a very small hump here, which is the zero phonon line of the material, and then a very wide phonon sideband. It turns out that this very wide phonon sideband is why this material is not a very good defect for quantum cryptography applications, but that's a whole different story. We can then look at our sample that we've doped with a silicon-containing small molecule, put this under high pressure and high temperature conditions, and we see a couple things. The first is that we still have this broad hump associated with the nitrogen vacancy center, but we also see this sharp peak that occurs at about 740 nanometers. And this is exclusively related to the silicon vacancy center. And it's confirmation that if we chemically dope silicon into that carbon starting material, we can form luminescent defects in the diamond. In reality, this is the first time that anyone's been able to, with solution chemistry, control the dopants that we introduce into diamond, which is a really impressive demonstration, I think. To confirm that we've made the silicon vacancy center even further, we can look at how this peak changes with pressure. So we've made this at some high pressure and high temperature. We can slowly decrease the pressure in our sample and watch how that shifts. So we've got a few data points, and we can measure a slope of about almost 1 MeV per gigapascal. And we went to some theoreticians in the chemistry department, and they were able to predict a very similar slope of how that zero phonon line should change with pressure. One thing that they were able to do that we couldn't do is take this up to a much higher pressure. So now go from about 25 gigapascals way up to above 100 and predict how this line should change. You could imagine actually reading this backwards now, where if you wanted to know what the pressure was in the chamber, instead of using that ruby that we introduced, you could measure the zero phonon line energy, go back, and then measure out the pressure that your sample is loaded at. And if you look, this slope is very comparable to the actual slope of that ruby material, except it actually has a more narrow line width. In addition, ruby will begin to fail as a pressure sensor at high temperatures and high pressures. And so the results seem to suggest that this silicon vacancy center could be an attractive material for high pressure sensing. One remaining question is actually how these dopants are incorporated into the material. And to do this, we used high-angle annular dark field scanning transmission electron microscopy, or STEM-HADIF. In this image, the contrast, as okay as it is on this screen, is related to the mass of the elements in the image. So you can see these very small, bright points, which are some high Z elements in the image and could be our silicon dopants. To confirm this, we did a lot of EDS and EELS maps. And we saw one thing, which is that there's silicon. But surprisingly, we also saw that there's argon in our material. Now, this isn't still loaded at pressure. This is material that we've taken out of the diamond anvil cell, that we've put on a TEM grid, actually flown to DC, and then put it back under ultra-high vacuum. So there's no way that argon should still be sitting on the surface. Really, this indicates there's some argon that is trapped within the diamond lattice, and presumably inducing some strain on the material. It can't just be sitting there innocently. And we can also observe this in the EELS spectrum. So it's very clear we have multiple data points that there's argon trapped in the lattice, which means that perhaps the overall picture looks more like this, which is that we start with some kind of doped amorphous carbon material. There we go. I always wondered what would happen there. We start with some kind of doped amorphous carbon material, and we have some kind of high-pressure argon environment, and that argon is incorporated as we heat at these high pressures and high temperature conditions. This means that this statement that argon and generally noble gases are great pressure media because they're chemically and physically inert maybe isn't so true anymore. And this goes against really 50-plus years of high-pressure research. And we think it could be a reason why groups have seen a lot of strange hysteresis effects whenever they've tried to pressurize and depressurize materials in phase transitions. Another note is that some groups are actually trying to incorporate noble gas defects into diamond. For example, xenon incorporated into diamond has been proposed as a single photon emitter for quantum information applications. And so this could be a new way of introducing those defects into diamond as a totally separate synthesis pathway. So I'm going to stop this portion of my talk here and just summarize that I've been able to develop this new method where we could dope a very covalent lattice with a very low diffusion coefficient by introducing the dopant within the material. We think this sets the stage for producing much more interesting polyatomic defects with small molecules. And this really could be a very useful platform for developing new defects for new kind of quantum computing or electronic applications. Similarly, this silicon vacancy sensor seems like it could be a better pressure sensor than the industry standard right now of Ruby. We also did some other research that I didn't talk about here, which seems to suggest that depending on the rate of heating, you can form other phases of carbon, but this still needs a bit more verification, really. So we return to this slide. On the right here is a very different system. So we've talked now about this case where your lattice has a very low diffusion coefficient. That is, it's very hard to get elements to diffuse into it and form the desired defect. In the second case I'm going to talk about, we're trying to introduce trivalent metal dopants into this inorganic perovskite lattice, which is shown here. This is composed of cesium and lead and chloride. And in particular, we're trying to form a very unique defect in the material that enables these to be used as down conversion. This is a material that's going to absorb high energy light and then re-emit a low energy light that's more appropriately used in solar cells, which generally is not the typical role of these luminescent materials. So first, this is now going to be motivated by solar energy, so I want to talk briefly about the current state of solar. We've spent a lot of time as a community of scientists, and really the world has come together and acknowledged that anthropogenic climate change is real and that we need to try and mitigate the temperature that the Earth rises. To do this, the primary pathway is to decrease the amount of CO2 emissions from our energy sources. There are a few different possible pathways to do this. For example, this gray bar is the amount of total CO2 emissions that are generated by fossil fuel. And in all of these pathways, to limit our Earth to a 1.5 degrees Celsius rise, we have to almost completely eliminate our use of fossil fuels. Failure to do this is not great. If you look through these IPCC reports or some of these papers, the results are pretty dire. If you look, 74% of worldwide population could be exposed to deadly temperatures for at least 20 days a year. By the year 2100, we could lose about 13% of our current land, which happens to coincide largely with where human population lives. And our ability to produce food will decrease significantly due to severe droughts. Now, one way to change this is to introduce a significant amount of low-cost, carbon-free electricity and power sources. In all of these pathways, really, we need to have about 70 to 85% of non-carbon-based electricity sources. And among these, solar is perhaps one of the best ways to do this. If you look at this graph, this shows the projected total installed PV capacity in terawatts as a function of different kinds of approaches. The important bit here is that this blue line shows us reaching the highest installed capacity if we target, in particular, high-efficiency solar rather than low-cost solar. You can imagine that the important characteristic for installing solar is the dollar per watt cost. We've done an incredible job at reducing the dollar cost of solar cells to the point now where most solar farms, the primary costs are the land you're putting it on. The glass, oftentimes in the solar panel itself, costs more than the solar cell you're sticking into the device. So just making the cell cheaper is not going to change this equation. What we're left with is simply making the solar cells more efficient. However, there's some challenge to that. On the top right here is the silicon solar cell power conversion efficiency as a function of year. And as you can imagine, we've steadily gotten better at making silicon and processing it. And these are two different silicon technologies. And I think it's attractive to try and draw these lines and imagine these are going to keep going up and up and up. But there's a fundamental limit to the efficiency of a silicon solar cell or any general solar cell. And thus, to enable some kind of new technology, we really need to find a way to change that ceiling. We simply can't get much further in our improvement. And if you look at now this graph as a function of the maximum achievable power conversion efficiency, you'll see that we're at maybe about 90% power conversion efficiency for silicon right now. There's just not much further to go. And if you look, all of the relative increases in power conversion efficiency have been very small, 1% boosts in efficiency, maybe even less than that over the past 25 years. Now, thermalization is responsible, is a phenomenon that's responsible for a large portion of the lost energy in these solar cells. Now, if you shine energy on a piece of silicon, or if you shine a light on a piece of silicon that's directly at its band gap, you will promote an electron into the conduction band, and then you can harvest this excited electron and hole as power. The power you generate is always related to the band gap of the material, or really the quasi-Fermi splitting of that material. If you were to shine yellow light on your sample, this will excite, but this excited charge carrier will rapidly thermalize in your sample, meaning that you've now lost a bit of energy to heat in the lattice. And this only gets worse as you excite with higher and higher energy light in the sample. In total, thermalization accounts for about 30% of the lost potential power conversion efficiency in a silicon solar cell. You can see that here whenever we have, you can predict the power conversion efficiency or the maximum achievable power conversion efficiency as a function of a solar cell's band gap. As you move to a wider and wider band gap, and here's the distribution of photons from the sun, you'll end up harvesting fewer and fewer individual photons from the sun, but collect them at a higher potential. That is, you'll have a higher voltage, but a lower current. On the other hand, if you go too low in your band gap energy, you'll end up harvesting a significant amount of photons, but the potential they're all captured at becomes very low, and you end up having these massive thermalization losses. Now, one way, this is in general a problem for photovoltaics. One way to potentially boost the efficiency of solar cells is with down conversion. This is the idea. To motivate that, let me show you some external quantum efficiency data. Whenever you look at a solar cell, its efficiency is different depending on the color of light that hits the solar cell. You can see in this graph that near-infrared light that hits the solar cell is very efficiently converted into power. And this external quantum efficiency is really the ratio of the collected charge carriers relative to the number of incident photons on the sample. If you look at high energy emission, it turns out this is actually very efficiently absorbed by the silicon. In fact, it's so efficiently absorbed that it absorbs right at the top of the silicon where there are a lot of defects, and it can easily recombine and be lost as inefficient energy. A way to overcome that is to add some kind of luminescent down conversion layer. This is a material that would absorb this purple or blue light, this energy that's used very inefficiently by the solar cell, and re-emit it at another wavelength. For example, perhaps green or red in this region over here. that is much more efficiently used by the solar cell itself. So you can imagine that perhaps you'd want to put a material, and this is just a fictitious material, that has this dotted line absorption spectra that would turn on, absorb all of this light, and then re-emit it at a lower energy. The ideal device performance would then look something like this, where rather than your EQE dropping off, all of these blue photons would be converted and then more efficiently used by the solar cell. The problem is that this really just gets us closer to that limit of the power conversion efficiency of a solar cell. It's still just a single junction, and you don't overcome thermalization in this device. So that there's a fairly exotic mechanism that would allow us to overcome this, and this is something that's known as quantum cutting. Materials that quantum cut absorb high energy photons and then re-emit 2 lower energy photons. If this was possible, you could then increase your external quantum efficiency, where every absorbed photon in the blue or purple region is re-emitted at a lower energy, and you're able to achieve twice the photocurrent. In this case, it would be like converting that excess voltage that's typically lost in thermalization into excess current as a way of boosting the efficiency and overcoming that single junction limit, in particular as a way of overcoming thermalization. And so our ideal device would look something like this, where all of a sudden, if the material can emit twice as many photons as it absorbs, we could produce twice as much photocurrent, and our external quantum efficiencies could approach 200%. In general, and maybe no surprise, this is enabled by dopants in materials, in particular in ytterbium dopants. So in the desired defect structure, we would have some kind of wide bandgap material. We could then excite it. This would, of course, thermalize. But then rather than emitting radiatively, this would transfer energy into 2 local defects within the material itself. These could then re-emit, and this emitted energy could be transferred to the solar cell. In this way, we've been able to convert 1 blue energy, or 1 blue photon, into 2 absorbed red photons in the sample. And as I mentioned, materials that have this property, for a wide variety of reasons, are fairly isolated to ytterbium dopants, or at least as a material that has this property in the visible region. One problem with this is that in order to transfer that high energy absorbed photon to 2 local defect states, they have to physically sit close to each other to be in electronic communication. This means that we have to form this kind of defect that I talked about earlier, where you have 2, for example, ytterbium atoms sitting very close to each other in the lattice. In addition, the ideal ytterbium host would have a very strong absorption cross-section. Ytterbium itself, this F to F transition, is electric dipole forbidden, meaning that it's a very weak absorber. This means that ideally, another material, the host that we put the ytterbium in, is doing all the absorbing. If, for example, you didn't have an absorbing material, it would take about a 1 millimeter thick film of ytterbium to absorb 99% of the photons, which is immediately going to be cost prohibitive. We also want our ideal ytterbium host to have a tunable absorption that would let us match different kinds of solar cell technologies. And ideally, we want to have a photoluminescence quantum yield of 200%. That is the number of photons emitted divided by the number of photons absorbed. And then finally, we want to ensure that whenever we put this material onto a solar cell, it has perfect sub-band gap transmission, meaning that all light that hits it, that isn't absorbed, passes straight through it. But we've really never had a material that does really any of these properties before. That was until about 2 years ago, where a paper from the Song group came out, and then a paper from my postdoc group came out showing that we can introduce these ytterbium dopants into this cesium-lead chloride host lattice. In an undoped sample, this material has a very sharp absorption with an exciton peak, and then this very sharp, very slightly Stokes-shifted luminescence. This original formulation here was made with nanocrystals. However, whenever we introduce the ytterbium, we see a big change. All of a sudden, this exciton luminescence completely died away, and it appears that all of the energy was transferred into this near-infrared region. And this is very characteristic of ytterbium luminescence. If we increase the amount of ytterbium in the sample, we see that as we increase it, this exciton luminescence goes away, indicating very rapid energy transfer to ytterbium defects, and that as we increase the ytterbium more and more, there's just increased amounts of this near-infrared luminescence. Also, if we measure the photoluminescence quantum yield of our sample, we see that this does begin to rise above 100%. This was the first paper that looked at this, but since then we've been able to make materials with photoluminescence quantum yields that are really approaching 200%. I think the highest we've measured is around 190, 195. And so this is really remarkable. This is the first material that has all of those properties after we've been trying to search for something that has these properties. I think it was first proposed in like the 1950s. So it's 70 years later that we found a material that can practically do this quantum cutting and potentially boost the efficiency of solar cells. The other unique part about perovskites is that they have an incredibly high diffusion coefficient. If you introduce any other atoms into the lattice, they'll freely diffuse, and these can let you vary the absorption and emission properties from red all the way through into the ultraviolet. We can use this to tune the absorption of our material itself. It's a little cutoff, but as we tune the absorption, here's a plot of the ytterbium emission in our sample. As we go further and further into the red, we see that this emission stays very bright, indicating that as we absorb more and more photons, as we shift the band gap down, that we're still able to quantum cut, and now we're able to absorb more and more of the solar spectrum. This means that for the first time, we now have a material that has this strong absorption cross-section. This means we can also tune the absorption to match silicon and have this very high photoluminescence quantum yield. Some last goals are still, can we make this with a very perfect sub-band gap transmission? Can we actually coat this on the silicon solar cells, which have very strong texturing to them to enable very high light absorption? And overall, what kind of efficiency gains could we expect to achieve? First, I'll address this question, and I'll try to move quickly through it. The ideal quantum cutting device till now, groups have considered this. It's been a theoretically proposed thing, but no one's ever been able to make a real device from it, and that's because no one ever had any real device properties. And so every paper to date more or less looked like this, where they said, all right, if we tune the band gap of our material and we tune the quantum cutting material, what efficiencies can we get? And this predicts that you could reach a very high efficiency. Now we've raised this bar from 32% up over 40%. However, this changes whenever you have real materials that don't always operate at 200% quantum efficiency. As you decrease the quantum efficiency of the material, it can become less efficient to absorb more and more and more of that light. And in fact, it suggests that the ideal material for the ideal solar cell for realistic photoluminescence quantum yields is at about 1.1 eV, which is exactly where silicon is. So this is convenient for us. But does the response of these silicon solar cells actually match with the material? You can imagine that the most important parameter for this is how well the silicon solar cell, or whatever solar technology we're putting this down conversion material on, behaves at the emission of our ytterbium. That is, how well does the external quantum efficiency of different solar technologies behave at these regions. And you can see that if you move from the silicon heterojunction, shown in the yellow, to a multicrystalline silicon, this behavior does drop. And so this indicates that maybe we want to target silicon heterojunction. And if we look at the maximum possible achievable efficiencies, I won't go through this graph too much, it seems to indicate that we can get really almost over a 5% boost in the power conversion efficiency. If we return to this graph at the beginning, this means that for the first time we could have a massive boost in the efficiency that goes up 20% all of a sudden if this device works. It also raises the bar for the maximum achievable overall power conversion efficiency of the device by introducing these new physics. Now the challenge is that as great as this may be, nanocrystals, really the ligands in nanocrystals, are not going to be cost competitive for being introduced into these silicon solar cells. And so we need some kind of other formulation. About the time that I joined the group, a postdoc in the lab showed that this actually isn't something that only occurs in nanomaterials. This can also be extended to simple solution process thin films. Here we're showing that you can vary the amount of ytterbium, and you can make these thin films that have very bright ytterbium emission and also quantum cut. We also did a fair amount of research and ultrafast spectroscopy to determine that this process occurs by this ytterbium-induced defect, which competes with photoluminescence of the material itself, but I'm not going to talk about that in great detail. Overall, these results in total, the fact that we can successfully produce this quantum cutting defect with solution chemistry shows us that the quantum cutting defect is likely the lowest energy structure, or that it does seem to form spontaneously, and that we can use this diffusion to help form the material. It also shows that physically, in the energy scheme, it appears to be the lowest emissive state, meaning that the energy will always reach it, which is convenient. It also really highlights that apparently just mixing ytterbium into this batch and heating it up can form this defect structure, which is not obvious. The challenge is that we needed perfect sub-band gap transmission. That means that all light that's not absorbed by the quantum cutting material needs to transmit straight through it. But if we look below the band gap here at about 400 nanometers, you'll see that there's this very efficient scattering that's going on, which is not going to improve the efficiency of the solar cell. Compounding with this, whenever you look at silicon solar cells, all these pyramids are what the surface of these materials look like. And so trying to make a smooth, even film on top of a silicon solar cell is challenging. But we know that this defect seems to form really easily, so maybe it'll just form fairly spontaneously in other ways. So we thought, why not just try and grind this together and see if we can make the material? So if you quite literally take lead chloride, cesium chloride, and ytterbium chloride, is this defect perhaps so energetically stable and the material have such a high diffusion coefficient that you can just form the material? And so if you grind these together, we see that we do indeed form some clear chemical change, and this looks a lot like cesium lead chloride. If we then look at XRD patterns, we see that it seems like just taking the materials, grinding them together, we've got an incredibly phase-pure powder as a product. We can then look at the photoluminescence of this. It's hard to look at the transmission because this is clearly has large grains and is fairly scattery. But just upon grinding this material together, it seems that we've sensitized this incredibly bright ytterbium photoluminescence. Again, this material didn't exist in any form 3 years ago, and now it seems like if we just mix them together in a jar and hit it, we formed ytterbium doped perovskite that quantum cuts. We can also do this not just with cesium lead chloride, but also with mixtures of cesium lead chloride. So now we're able to balance really a 4-element species by just grinding it together and produce this material. Now, the challenge is that and I should say this chloride bromide material also shows this very strong sensitization. The challenge is that this is not, I mean, we've made this powder. This perhaps illustrates just how well we can form the defect, but it's not transmissive. We're not going to spread a paste of this powder on top of a solar cell. One way to potentially get around that is to evaporate the material. It seems like this material forms the desired defect incredibly easily in almost every other case. So what if we just took that single source material and heated it up? Perhaps this would give us better transmission properties and let us conformally coat onto those textured silicon pyramids. So we can take our powder. Again, this looks to be phase pure from our XRD. And if we evaporate it onto a film and do XRD, astoundingly, we seem to form all of the right peaks. That means taking just this powder, this single source material, and heating it up rapidly, all of the phase diagram is appropriate, apparently, that whenever it hits a substrate and the vapor pressure, whenever it evaporates, hits the substrate, we form the right material. And if we look at the photoluminescence of this material after annealing it slightly, we see this very strong emission characteristic of ytterbium in this evaporated film. This is incredible that just heating up the powder that we've physically ground together seems now to give us what looks like a quantum cutting material. And indeed, the photoluminescence quantum yield of this sample is 183%. If we look at the desired absorption properties, we needed something that had almost perfect sub-band gap transmission. And if you look at this now, we have optical densities that are above 4, and below that, almost perfect sub-band gap transmission. So this is exactly the material we need for quantum cutting. In fact, this is so flat that you can see these small interference fringes in the material, which are characteristic of light interfering with itself as it bounces through the sample. And if we look back, we need really that exact flatness to achieve our ideal downconverter. And this isn't just limited to this ytterbium-doped cesium lead chloride. This works with the chloride. We find this also works with a mixture of the chloride bromide. So now, astoundingly, just putting these in an evaporating source and heating this up either slowly or rapidly, we can form apparently incredibly transmissive and ytterbium-doped films. This also extends to what I think is known as the kitchen sink perovskite. This is formidinium, methylammonium, cesium, lead, chloride, bromide, iodide. If you stick all of those together in a mortar and pestle and grind, it seems like you form the ideal XRD powder, or X-ray diffraction material, and that then you can rapidly evaporate this and form, it seems like the right film. And this is also extended to very large areas. So this is a 6 by 6 inch piece of glass that we've coated with this material, and we're shining a near-infrared LED diode at the material. Now, in theory, if it's emitting near-infrared light, which we can't see easily with our eyes, and so we can use actually night vision goggles with a small band pass to only look at ytterbium emission from these, and we see this incredible glowing film. One sort of interesting property that you see is very clear waveguiding to the edges of this sample. This wasn't an initial goal of ours, but it seems like this could be a really useful material and method of deposition for a device called a luminescent solar concentrator. This is a material, or this is a device where you would have a large piece of glass with a luminescent material, and then you stick solar cells in the very edges of it. This way you can put very high efficiency solar cells only in a very small part, but absorb a wide range of the solar spectrum. The other key bit to this is that these do seem to conformally coat silicon. If you look, the perovskite layer that we've deposited on these, here's about 150 nanometer thick ytterbium doped cesium lead chloride film. This smoothly fills in with very even thickness throughout the valleys and peaks of our material, which just would not happen with a solution process material. As part of this, we've formed a company to try and commercialize some of this work. We think it's really exciting. It has a lot of potential benefits for the future of solar. In particular, we're looking at both this quantum cutting material and this ability to rapidly deposit perovskites conformally onto silicon. And with that, let me just quickly summarize where we started with this. It seems like we found really the first material that can quantum cut, and because of its ability to form because of the fact that the quantum cutting defect seems to be the lowest energy structure, and the fact that this material has an incredibly high diffusion coefficient, we can use those properties to engineer a wide range of different applications, and those applications are very scalable in a wide range of processing steps. We think that's going to make for some very efficient solar cells and for some very efficient luminescent solar concentrators. With that, I'll thank a lot of different people, a lot of my PhD group who were instrumental in all of the diamond work that I talked about at the beginning, as well as many different collaborators, and then my postdoc group here showing us in our quantum dot t-shirts varying from blue out to black. Everyone whose names were highlighted there were incredibly helpful in this project. And with that, I'm happy to take any questions.